Thanks everybody for coming to today's edition of the Quasiworld. So our first speaker is Raanan Schul, and he will answer the question when a metric space is uniformly rectifiable. So please, Raanan.
So thank you for the invitation. So everything I'm going to talk about today is joint work with David Bate and Matthew Hyde. Of course, I take full responsibility for any errors I might make today. I'll mention some of our previous work, which has already been made public, but a few things that I'll talk about are work in preparation. I'll point out when this happens. Okay, so maybe I just feel I need to give some background. We have a metric space, specifically some subset of Euclidean space. And we were going to assume that the Hausdorff dimension in is K, and we're going to say that it's K rectifiable if all the mass up to some negligible set is captured by a countable union of either Lipschitz images or BiLipschitz images. There are various equivalent characterizations. And the way I like to think of it is that E, if you remove a null set, has Lipschitz charts. So it's sort of the analyst version of topology. And there's old results that say that you're K rectifiable, so rectifiable of dimension K inside Rn, if and only if you have a tangent almost everywhere, and there's various notions of tangency that make sense, and if and only if you have a density almost everywhere. So I'm going to talk about both of these today, but the goal is going to be to talk about the metric setting. In Euclidean setting, the relevant names to mention are Vesikovich, Marstrand, Motilla, and Price. I'm not sure how much I should talk about this, but so I'm going to talk about uniform rectifiability mostly, and that has some history, and that has to do with L2 boundedness of singular integrals in the plane. So the motivation was what was called Pan-Levé's problem. In 1977, Carleson showed that some singular integral has an L2 bound if the space on which it's defined is a graph of a Lipschitz function where the Lipschitz constant is small. Then a few years later, Koifman, McIntosh, and Meir said, well, we don't really need a small constant. And the reason I'm mentioning this is because this property, this singular integral being bounded, is stable under what's called big pieces. So I want to tell you what big pieces are, because that's going to be an important player for me. So we're going to assume that our sets are all first regular of some fixed dimension K. And later on today, K is just going to be decidedly 2. So we're going to fix some all first regularity constant, meaning that the K-dimensional area of a ball is bounded above and below by R to the K times a constant. And we're going to have a family of sets which we're going to think of as nice. They're going to be graded by scales. They're all going to be all first regular of dimension K with some fixed universal constant. And we're going to, so having big pieces of this family F, actually I wrote it like this here, big pieces of this family F, means that there's some constant theta, so that if I take any ball, right, so a center and a radius, and there exists some set, which I think of as nice inside this ball that captures at least theta of the mass. So think of theta as a small constant, say 3% of the mass is captured by a nice set. That's what it means to have big pieces of F. And so in the previous work about about singular integrals, so the nice sets were Lipschitz graphs with small constant, and it turns out that Lipschitz graphs with small constant are so Lipschitz graphs of well, okay, so you can bootstrap that going up. So let's just talk about Lipschitz graphs, not Lipschitz graph of small constants. So fix some constant with Lipschitz graphs. You can talk about sets that have big pieces of Lipschitz graphs. You know, talk about sets that have big pieces of Lipschitz graphs. You talk about sets that have big pieces of big pieces of big pieces of big pieces of Lipschitz graphs, and so on. And this turns out to stabilize. So the biggest you can get with this is big pieces squared of Lipschitz graphs. A special nice family F is what is called Lipschitz images. So having big pieces of Lipschitz images means that your script set F is of this form. Sorry, I should circle this form. So big pieces of Lipschitz images means that for every ball, meaning every point and every radius, there is a Lipschitz function going from the ball or the cube in k-dimensional space into Rn that captures at least theta of my ball. Right, so you think of this as big pieces with parameters where big is denoted by theta, and Lipschitz image means that you fix a priori the Lipschitz constant L. And it turns out this is equivalent to what's called big pieces of BiLipschitz images, where the same thing is true, except you replace Lipschitz with BiLipschitz. It's useful also to replace this with subsets of the ball, but that's that will come back later. Any questions so far? I guess I should say that people should feel free to interrupt me with questions. Okay, so Guy David and Stephen Sims prove the following. So they prove that if you assume a priori that a set is all first regular of dimension k, then these following properties are equivalent. So let's start with property 2. Property 2 says having big pieces of Lipschitz images is equivalent to having big pieces of BiLipschitz images, equivalent to having big pieces of Lipschitz graphs. It's also characterized by what's called a geometric lemma. I'll get back to that later. It's equivalent to these goodness for singular integrals. So it's on the plane. This has to do with what I briefly mentioned earlier. And properties 4 and 5, I guess this is more dramatic like this. Properties 4 and 5, I'm going to talk a lot about today. So one of them is that E has what's called a corona decomposition, and the other is E has a weak constant density condition. It's worth noting that weak constant density being equivalent to all of these things is for codimension not equal to 1 or dimension not equal to 1 was proven by Tulsa in 2014. Okay, and any of these properties is what's called being uniformly rectifiable, since they're all equivalent, and there are many other equivalent definitions. Somehow there's a lot of different nice characterizations of uniform rectifiability. So I'm going to get back to talking about these guys, but my goal is to talk about metric spaces. So I want to first talk a little bit about metric spaces. So we're going to assume that we have a metric space X and that it's all first regular of some fixed dimension. And so what are examples? So you could take, say, the plane with an L1 metric. So of course that's by Lipschitz to R2. Or you could cut out a bunch of squares from different LP spaces and sort of stitch them together into a quilt and then take a path metric. So that's sort of what I want you to have in mind when you think about a metric space for now. And the reason I'm saying this is because Kirchheim proved in '94 that if you have a Lipschitz image from Rn to X, so again, imagine that n equals 2 here, then you can approximate the metric in the image. This is supposed to be the distance in the image. I wrote it as absolute value. So if you can approximate the distance in the image by a semi-norm on the domain. So this guy is a semi-norm on the domain. So in that sense, you have differentiability almost everywhere. And you can deduce two things from this. You can deduce that you can break up F into a bunch of BiLipschitz pieces. sort of in a qualitative way, and you can deduce that the density of the image exists almost everywhere. Okay, and then a converse to this was proven only recently, so a few years ago, by David Bate, and he says that the property of having a tangent almost everywhere implies that your space is rectifiable. So this idea of having a tangent almost everywhere, and this tangent being a Banach space. So David Bate says you have a tangent and it's a Banach space, implies it's rectifiable. So this idea of having a tangent almost everywhere, and this tangent being a Banach space is a characterization of rectifiability. Notice that I did not say anything, right? So this theorem has two conclusions, one about metric derivatives, so Banach space tangents, and another is about density. In the converse direction, I never mentioned density. This is something that I will talk about later today. So a lot of work went into the following theorem with David Bate and Matthew Hyde, and that's that if you assume a priori that your metric space is all first regular, then we have an analog of some of the work that the Wittgensteins did. So we have equivalence of the following condition. One is big pieces of BiLipschitz images, or you could also add to this big pieces of BiLipschitz images. Another is having a Carleson conditions on balls where they are badly approximable by Banach spaces. And I will talk a lot about what a Carleson condition means. And the last two conditions are having corona decompositions by some families of sets. And I will also talk, right, so there's two notions here that I'm not defining yet, right? Carleson condition and corona decomposition. So I will get back to these in a few minutes. Okay, Carleson condition. So what is a Carleson condition? It says the following. I look at all balls that are bad in some way. So here, bad for me means that I am not epsilon approximable to approximate. I don't have an approximation up to error epsilon scaled by the radius by a Banach space. Okay, so this is what in the Gromov-Hausdorff metrics, this is what bad means, but it doesn't matter. It means some collection of balls were deemed bad, and a Carleson condition means that I don't have too many bad balls. In what way? If I look at any ball in my metric space and I average over it, in the sense that I look at all possible points in it, and when I look at all possible radii between 0 and the radius of this ball, but I weigh them equally. So I integrate the R over R. Right, so I average over points, and I integrate the R over radii, and I either take 1 if I'm a bad ball or 0 if I'm a good ball. So saying that I have a Carleson condition says that this big integral is bounded by 1. And this bound can depend on epsilon. And in a few places today, I'm going to talk about a weak condition. And by weak, I mean always that I allow, that I only look at things that are bad up to epsilon. Like this. So I say they're at least this bad, and then I allow my bound to depend on epsilon. Sort of like what you get when you prove weak 1-1 conditions in LP spaces. Talk about various operators. So this is a quantitative way of saying that if I look at points that are in an infinite collection of balls, sort of with radii shrinking, then this set of points that are in an infinite collection of balls going down have measure 0, right? So this is what I wrote here. Okay, but this is done in a quantitative way. Okay. Okay, so I'm gonna go on unless there are questions about this. So I said that we want a density characterization of uniform rectifiable spaces. This is inherently not feasible because if you take the real line and you take this metric on it, the square, the snowflake, then every ball has measured exactly r squared. And certainly this is not a rectifiable metric space. So something here went terribly wrong. And so what we're going to do is we're going to restrict the topology. So we're going to say that we're talking about two-dimensional spaces, both in terms of topology and in terms of measure. So we're going to talk about planes topologically. And also what we're going to do is we're going to restrict the dimension. Specifically, we're going to, again, talk about planes. And in the back of your mind, you should know that David Bate has a paper where he says that if you have density equal exactly to 1, he has a characterization of all possible spaces that can come out of that, all possible metric spaces. And if you assume that you're also topologically the real line, then of his 3 options, this is the only option that stays. And the question is, what do you know if you assume that, well, one question is, what do you know if you assume, I made a mistake here, it should be H2 of a ball is R2, and you also assume that you are a topological plane. Can you get that you're R2? So initially that was something that we were asking, but
Raanan, a quick question. When you say something is equal to R or equal to R2, you mean with the Euclidean metric, right?
I mean, yes, with the Euclidean metric, absolutely. Right. So yeah, if I just write this, I mean with the Euclidean metric. Thank you. So we're not going to see that things are equal to R2, but we are going to see that they're uniformly rectifiable. So here's the plan for the rest of the talk. We're gonna, well, this is a weak version of the plan, but really what we're gonna do is we're gonna show this, but I haven't defined exactly what this means. So the plan is to start with a geodesic plane, right? To assume that X is a metric plane and that the metric is given by geodesics. And then we're gonna say if it has constant density, then it's actually locally linearly connected. And then we're going to show that if it's locally linearly connected, then it's uniformly rectifiable. Well, that's a lie. We're not going to show this. This was shown by Guy C. David 15 years ago. I think he's in the audience, so he can tell me how long ago that was. I guess Mario, you should also know. We're going to do better than that, right? So we're going to show that if you have weak constant density, then then you satisfy what we call weak LOC. So I'll say what that means. Well, I'll say what that means later, but I can just tell you now. This means that so weak constant density means that balls that fail to have constant density in some quantitative way satisfy a Carleson condition like we had before. Weak LOC is going to say that balls that satisfy to be contractible within some fixed constant times the radius are also rare in that they satisfy a Carleson condition. So we're going to show this, and then we're going to show that weak LOC implies uniform rectifiability. And I will remind you later that uniform rectifiable metric spaces have weak constant density, which will make more sense maybe after I define what weak constant density is. That's a theorem by Jared Crandall. Okay, so I mentioned the theorem by Guy, so let's state it. So Guy's theorem, okay, sorry, 2016, so 10 years. So if you have an all-first regular topological d-dimensional manifold, which is locally linearly connected, complete, orientable, then it is uniformly rectifiable. In other words, if you're fully LLC, then you're uniformly rectifiable.
So quick question.
Yes.
I'm a little confused by this LLC. I mean, do you mean locally uniformly contractible, maybe?
Yes, I probably said connected and not contractible. I often say the wrong thing.
But in
Yeah,
dimension two,
D is
they're
contractible.
kind of equivalent, right?
Yeah, sure, but I mean, your theorem now is stated here for D manifolds, right?
Yeah, yeah. Here it should be contractible.
It's always contractible for me.
And here, I mean, I think you said this out loud, Ron, but the all fours regularity has to match the D, otherwise, of course, it's not true.
Uh, sure. Yeah, sorry. Thank you. Yeah, sorry. Thank you for this. Okay, but we're interested in a situation where X does not necessarily have to be exactly C. So we're going to find this set B LCM. So this is going to be a collection of bad balls, and they're bad in the sense that a ball that said specific ball is not contractible within m times that ball. Okay, so those are our bad balls. And Guy's theorem is, of course, about the situation where this is empty for an appropriate choice of M. So we're going to say that we're going to be interested in a situation where these balls, these bad balls, satisfy what's called a Carleson condition. So just like before, if you look at any ball and you look at all sub-balls inside it that are bad, and you sum them up in this way, then the sum is controlled. And of course, there's a constant hiding here, and the constant is allowed to depend on epsilon and on the badness that we allow the LLC, but it's not allowed to depend on the big ball that we're looking at. Okay. And truth be told, is we always end up working with a dyadic version of this. So I think probably everyone in the audience here knows about the existence of Chris cubes, and that you can always rewrite this in a dyadic way along Chris cubes on some tree. So if you have a cube R and you look at all of the cubes that are either inside it or inside its triple, and you look at all the bad ones, then their volume is controlled by the volume of R. And really all I did is I rewrote this in a dyadic way. Any questions? Okay. Okay, so we're gonna use these bad cubes to construct what's called a corona decomposition. So I'll tell you what it is in great detail in a few minutes, but the first thing I want to say is that we're going to look at the tree of all possible cubes that Chris gave us, and we'll decompose them into subtrees. And each subtree is going to have associated to it, or approximated, it's going to be approximated by a well-behaved space. So the underlying set in it is going to be approximated by a well-behaved space. So I'll say more. So what is a corona decomposition? So there's going to be a few slides now that explain this. So I want to think of my space for a minute in terms of its dyadic decomposition, and a good model is think about the unit interval being, decomposed of dyadic blocks at all different scales, and this gives you some tree, and it has some good cubes and some bad cubes inside this tree. So here I drew some of these were green, so they were good, and some of these were red and they were bad. Okay, and I'm going to think of cutting this big tree. And so every time I see a bad cube, I take my scissors and I cut. So I'm going to cut here, and I'm going to cut here, and I'm going to cut here, and so on. And I get a bunch of connected components, and those are my subtrees. So the good cubes end up being the union of these subtrees, and we're going to be in a situation where we can assume that we have not too many bad cubes in the sense that the bad cubes satisfy a Carleson condition. So maybe I'll go back to this picture again. And what's going to happen in the next slide is that we're going to say that a set has a corona decomposition if each good tree, so if this orange thing that's here is in some sense, will approximate it by a good set. And we need to decide what good sex means. But let me just say that I'm not saying that the tree is well approximated, and because that by a set, because that's a weird thing to say. I'm going to say that the leaves of the tree are approximated by this good set. So okay, so in RD, so this first came into existence in RD, and then I think David and Sams and maybe earlier Sams were the ones that did this in the 90s, in maybe 1990. So E has what's called a corona decomposition by Lipschitz graphs. It's usually denoted like this. If you fix a priori constants, so L is going to be a Lipschitz constant of the Lipschitz constant of the graphs. E is going to be the goodness of approximation, and C is going to be how many bad cubes you allow. And you have a decomposition of the tree into good and bad cubes. And if after I snip at all the bad cubes, I get a bunch of trees, and each tree has a good set GT, which is an isometric copy of a graph of a function that looks like this. So a graph at the right scale with a fixed Lipschitz map. And the graph is going to approximate the leaves of T in the sense that the distance between any point inside any cube in T, specifically a leaf as well, and G of T is bounded by epsilon times the side of that cube. So the smaller the cubes are inside T that contain X, the better the approximation. So it's not a uniform approximation, it's an approximation that gets better and better the deeper the tree is at that point. And we're also going to require that I don't have too many bad cubes. So in this Carleson sense. That's what it means to have a corona decomposition by Lipschitz graphs. But I'm in a metric setup, so I'm going to need to change this a little bit. But first, I wanted to say that having big pieces of BiLipschitz images is equivalent to having a corona decomposition by Lipschitz graphs. And that was one of the things that David and Sams proved. This is maybe a little bit too technical for this talk, so let me skip this. Let me just say that this allows you to change the Lipschitz constants in the approximation at will by paying a price of having more bad cubes. So this is maybe a technical thing. Right, and Sams 1990 and David and Sams 91. One of these things were introduced. I need to talk about metric spaces though. So if you fix a metric space and you look at the dyadic structure on it, given by Chris cubes, we're going to have a family F of good sets. So these are all going to be alphas regular of some fixed constant. We're going to say that X has a corona decomposition by these sets, by these good sets F with, I'm going to have two parameters, lambda and theta. If I have a decomposition into good and bad cubes, and I can write the good cubes as a union of these trees after I've snipped at all the bad cubes. And I don't have too many bad cubes. And this is the analogous thing. If I look at the roots, this is a root of a tree. If I look at the roots of all trees, they don't have too much volume. If you really cut exactly at the bad cubes, then these two sums are actually identical to each other. But there's some more flexibility that you need for technical reasons, but I'm not going to get into that. So you don't have too many places where you had to cut, is what this is saying. And any of these trees has an approximating set inside F and a mapping, right? So this is not, you can't say an approximating graph because, well, it's a metric space. So you need a mapping from the root to my good set, from triple the root to my good set, such that the distance in my metric space, the distance in my metric space is approximated by the distance in this good set up to this fixed constant lambda, right? So I got But I don't want this for any pair of points. I just want it to points that are well separated inside my tree. Okay, so this is what it means. This is a little bit of a mouthful, this description of corona decomposition, but it's sort of a fundamental tool that one needs. So, so what are useful families? So what are good families? So in the previous work that we had with David Bate and Matthew Hyde, we cared a lot about this condition, meaning studying the Gromov-Hausdorff distance from Banach spaces. And then a useful family of good sets was BiLipschitz images of RK. For today, a useful family is going to be LLC spaces. And specifically LLC spaces, because by Guy David's theorem, we have that those are uniformly rectifiable. Of course, with underlying topological assumptions, but we have those because we're a plane. Okay, so I started by saying I want to talk about density characterizations, and now is a good time to go back to talking about density. But I guess I want to ask first if there are any questions about this. We're good? Okay. Okay, so I need another collection of bad balls. Okay, so what is my collection of bad balls with the subscript density? So they're bad in terms of density. It's going to be you're a bad ball if you failed something, and the thing that you failed is this. So what you failed is that you failed the existence of two. So you need some normalizing constant and you need some epsilon. So maybe I'll write you're bad with epsilon naught and a bound on CXR. So C is not allowed to vary too much above and below. And what this is saying is that your density, there's no way to normalize your density so that it equals T to the K up to that normalization and up to this additive error. In other words, there are at least a few scales. So in the next, say, log epsilon scales or something like that, something with K, you're going to fail to have constant density. Okay, up to this additive error epsilon. Okay, so that's what it means to have to be bad for this in terms of density. So of course, if you have constant density, then this is empty. But we're going to allow more variation. So we're going to allow perturbations of having constant density here. So Jared Crandall proved that if you're uniformly rectifiable, then these balls satisfy a Carleson condition, meaning most balls have constant density in the right sense. And the theorems that I want to mention today, and this is where it really is work that's currently being written. So I think we wrote all the math, but there's still some paper still needs to grow by like 30% probably in terms of level of detail. Is the following statement. So if you are two-dimensional, so Jared's theorem was about all dimensions. But if you're two-dimensional and you're a topological plane and your metric is a geodesic metric and the bad balls for density satisfy a Carleson packing condition, then the bad balls for LLC satisfy a Carleson packing condition. That's the first theorem. And the second theorem is that if the bad balls for LLC satisfy a Carleson packing condition, and again, you're in dimension 2, you're a topological plane and you're geodesic, then you're uniformly rectifiable. So I want to spend the rest of this talk talking about these two things.
Can I ask a quick
So,
question, Raanan?
yes,
For your
please.
second implication, right? I mean, you assume that the space is geodesic, but it seems that the conditions should be fairly robust. For example, if you just have quasi-convexity, shouldn't you get a similar conclusion then?
So, okay, so that's a great question. So, the issue. So, okay, so certainly LLC is invariant under BiLipschitz maps, right? So if you take two, right, so if you have two metrics, one is the geodesic one, and one is given by quasi-convexity.
Yep.
So right, then so these two metrics are BiLipschitz.
Yep.
So it doesn't really so this theorem doesn't really see this reparametrization.
Yep.
Right? Because uniform rectifiability doesn't care about the BiLipschitz reparametrization. This guy doesn't care. But here, this guy does care about a BiLipschitz parametrization. And I actually don't know if right, so you give me right, if you give me a space where that okay, so let me say it this way. If you give me a space that satisfies that this is Carleson and is geodesic, then you go through this machinery, you get that it's uniformly rectifiable, then a BiLipschitz image of it is also going to be uniformly rectifiable, and then you're going to get that it satisfies this with the new metric. But if you told me that the non-geodesic metric had this, or the quasi-convex geodesic had this, then I don't know how to complete the picture.
I see. So, I mean, if I understand you right, my question is kind of trivial, right? Because for your second implication, I mean, it's obvious.
Which is second? This one, or so? How,
no, I mean the one below.
This.
I mean, there it's kind of obvious that you can replace the word geodesic by quasi-convex, for example, right?
Yes, because then you just reparameterize.
I mean, in the first, this is not at all clear as you argued, right?
Yeah. So for this guy, you just reparameterize.
Yeah.
For this, honestly, it's a little bit unclear, and I think it's interesting.
Yeah.
So you could. So this result, if you look at its proof, you could dig out and try and show that this thing is stable under BiLipschitz reparameterizations. For the plane that looks like it. Okay, for the plane, there are people, specifically most of the people in this room, that know a lot. And so it's not crazy to think that for the plane, it's possible. For other dimensions, this becomes even more mysterious. So the honest answer is I don't know even for the plane, but it wouldn't be crazy to believe that this might be true for the plane, and it's false for R3, for example.
Can I ask a question?
Yes.
Okay, so in the middle, again about the middle one. So when you say k equals 2, you mean it's all fours 2 regular? Is that?
I mean, it's all fours 2 regular to topological dimension 2.
So what's what's an example that I should something that's too regular, topological plane that's too regular and geodesic, that might not be LLC on some balls or might not have this constant density condition on every ball. Like, what should I be imagining? Because the usual thing is like a cusp, but then you're not going to be all fours regular.
I'm imagining, so I'm imagining a bubble with a small, that's sort of connected with a small neck, and a sequence of those. Where
will you be all fours 2 regular if you have these small necks? I mean, usually.
So the necks don't really have to exist. So let me draw. Let me zoom in. So I guess just place the bubble on top, and then you have some interface here. and right, so this interface was removed so that I'm still a topological plane, and then it is all first regular because the neck it's a very imagine the neck as being non-existent. Does that make sense?
No, but I can think about it.
Okay, let me try a little bit harder, right? So yeah, right. You take a bubble, you take a ball, you
Really?
place it on a plane, and then you just shave a little bit off the connection.
Oh, I see. Yeah, but
And then it's all first to
um,
regular. And depending on how much you
yeah, okay.
shave,
No, I understand. Thank you. Yeah. I was trying to
yeah.
imagine the correct thing. Yeah, I get it.
Okay, it's important for me that you understand this because I'm going to have a
Yeah,
badly
no, I
drawn
get it.
picture of what I just described on the next page, and we're going to want to talk about it. Right, so so depending on how much you've shaved, you've if you shave very little, your LLC constant is very large. And now you can have a bunch
Yeah,
of these
exactly.
balls really far away so that you don't screw up all first regularity. And right, so you have right a bunch of these balls. Um, and 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 you're not LLC. Okay. Uh, anything else? Okay, so this exactly is what I was trying to discuss before, right? So here I have a bubble that I've attached to my plane, and this is the part that I was saying that I've shaved. So I think of so 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 if this is a metric ball, right? Something that's here, of course it doesn't see this part, but in order to contract it, I have to go all the way to the top. Right? I have to.
Let me actually, sorry for interrupting again. Let me follow up on a guy's question, right? If I understand it right, I mean, the size of the neck does not somehow influence the alpha's regularity, right? Even if you make it
Correct.
very, very small, right? The alpha's regularity just doesn't see this.
Correct. So let me say that neck. I used that word, but as soon as I said it, I slightly regretted it because it's not exactly a neck. It's a, it's almost like a connected sum. Like you don't necessarily need to. I guess that doesn't matter in topology, right? But you just
Oh, I mean, we
plop the bubble
understand, we understand. I
onto
mean,
the plane.
yeah.
Okay. Um. Okay. So I claim so this picture, right? So if this violates LLC with some constant m, I claim that there's another ball that will violate constant density. And that's the point of this. So what is this other ball? So I look at the peak of the bubble and I look at this radius, right? So think of that radius as the distance to the original ball. And right, so this bubble, I think of it as it's what you need to do in order to compress this metric ball, right? So it's I call it the topological ball because I think of it as the bubble. And what does constant density for this ball tell me? If we perturb capital R a little bit, it tells me that this annulus here has mass, which is linear with respect to big R, right? So if you perturb R squared in this neighborhood, so big R goes from say hitting one side of this annulus to another side of this annulus, then the mass has to be linear with big R. But this perturbation can't. So if the ratio between the radii is too big, then this perturbation is all happens inside this little R ball, and then you get a contradiction. Okay, so if the big ball fails constant density, sorry, if the big ball has constant density, then sorry, if I'll say it the opposite way. If the little ball fails LLC, then the big ball fails constant density. Okay, so this requires some taking care of, and there's some topology, and this is one of the places where geodesic comes in. Notice that these are different balls. So it's not that if a single ball fails, if a single ball is here, then that same single ball is here. But if this is Carleson, then this is Carleson. So it's not, so you have to do some counting. And I guess that's what this slide says. Right? If this fails, then this fails, and eventually you get that if there are very few balls that fail LLC, there are very few balls that fail density. Okay. Now I want to talk about the second item, which was that if you have very few balls that fail LLC, then you're uniformly rectifiable. So the goal is to reduce the Guy's theorem, the Guy-Davis theorem. And so we divide into subtrees as one does for a coronization. So we switch to talking about data cubes, and we divide into subtrees in the same way that we did with constructing a coronization. And we can work a little bit on these subtrees so that they have the property that minimal cubes which are near each other, sort of like this guy, have similar sides. So that's a technical thing that one needs. And after we do this, there's this phrase that I wrote here. We take those non-LLC balls, meaning think of them as these bubbles. We cut them and we put disks there, right? So that's the plan. And this is another place where we really use the fact that we're talking about a two-dimensional geodesic plane. And I said this here, but when you write this down, it's about 30 pages to do this sufficiently carefully. And after you do this, right? So after you cut out those bubbles and you replace them with disks, you can then say, oh, now I have a coronal decomposition by LLC planes. And that means that I have a coronal decomposition by uniformly rectifiable spaces. And that means that I'm uniformly rectifiable. So somehow to get here, you use essentially Guy's theorem. To get from here to here, you use Guy's theorem. And then to get from here to here, you use our old machinery that we had with David Bate and Matthew Hyde. I want to say a little bit more about this phrase, cut out the non-LC balls and replace them with disks. Because there were a bunch of technical issues that came up that I just want to say what they are and not even talk about how to resolve them. So one issue is that, right, I have a ball, it's a metric ball, it could have holes in it. And the first thing you need to do is you need to talk about a Jordan domain and the plane that contains it. Okay, so that has to fill the holes. The issue is that the ball could have a boundary that does not look very round, right? It could be really not chord arc. And if I'm going to sew a disk into something like this and hope to get something nice, I don't know how to do that. Right, so I first want to say, hey, without loss of generality, there's a nearby bounding chord arc curve. And okay, so that's one claim that one has to prove. Another issue is that I could have this chord arc curve that I got, and then another chord arc curve, and another chord arc curve, and so on. So I'm going to separate them into families. Right, so this is one family in this picture, and I'm going to work on both of these together. They don't really interact with each other, but then I had this chord arc curve, and all of a sudden I changed the metric here. So I now need to change this chord arc curve somehow. And I need to make sure that I get a new chord arc curve. So every time I've changed the metric here, I need to go over all the other chord arc curves that I haven't yet dealt with and replace them. And then I do this for family A, and I do this for family B, and I do this for family C. And there's a finite number of families that I have to do this for. And after I do all of this, we're going to need to check that what you got is LOC, right? So you're going to take a generic ball, and you're going to have to contract it. And that's it. Okay, so that's the outline of the proof. And now I would like to switch to some questions that we don't know how to answer. So this was all in dimension 2. I cannot say anything about dimension bigger than 2. There's another natural collection of bad balls that one could imagine. One can imagine balls where the Poincare inequality is violated with some fixed constants. So years ago, Jonas Azam, not many years ago, Jonas Azam proved that in Rn, if you have no bad balls, that if the Poincare inequality is always holding with some a priori constants, then you're uniformly rectifiable. Recently, Jacob Laxer, he was a student of mine that graduated last year, he proved that if the bad balls for Poincare inequality are Carleson, then you're also uniformly rectifiable.
Sorry.
I don't know what happens for metric spaces.
Can I ask a quick question about this Bate or PI?
Yes.
So do you fix a function f, and for that, the
No,
Carleson
this
condition?
is for any function f. So
Okay,
you're
so
bad for PI
if there is some
if there exists a function f such that you're flexible over f and its upper gradient.
I see. Okay. All right. Thanks.
Okay. Right. So what is known for metric spaces? Okay. That's another sort of natural and related question. And then somewhat more technical. I don't know. So how many more minutes do I have? When should I stop
maybe
talking?
2 minutes.
Okay, so let me just say this was called a weak condition, right? Because we fixed some epsilon and we looked at where this is bounded by epsilon. In Euclidean space, there's what's called a strong inequality where you don't. I mean, so uniform rectifiable sets are characterized by this weak inequality, but more is known, meaning that if you're uniformly rectifiable, then you have a strong inequality, meaning you don't just, here we rounded up epsilon to 1, and we rounded down less than epsilon to 0. But in Euclidean space, you have something where you sum over all deviations from being approximable by a plane. So this is what's called the geometric lemma. It's something that looks, well, here I wrote down that controlling, so people usually call these beta numbers after Peter Jones's beta numbers. And the point is that you can use some ability of these numbers to characterize rectifiability. In metric spaces, if the dimension is 1, then you have this geometric lemma characterization. And this is recent work by Fassler and Violo. But I don't know, and I don't think anyone, as far as I know, knows how to strengthen this to allow a more delicate sum rather than just 1 and 0. And again, the upshot of knowing something like this would be that, at least in Euclidean space, one can use then sums of this type to characterize rectifiability. And we're just not there yet. So there's a a key result in Euclidean space, which is called Raanan-Schul's theorem, which is all based on, and the analog of Raanan-Schul's theorem here is just not known. So the closest result I know for this is being there's some quantitative estimate about being approximated by norms, but this is all for up to error epsilon, which is why the weak geometric lemma is what we can prove. Anyway, this is maybe another 10 more minutes of talking that I probably don't have. So maybe this is a good time to say thank you.
Okay, thank you very much. So let's thank our speaker. And let me start the discussion. So any comments or questions? So you mentioned that in higher dimensions all this fails, right? I guess.
Well, I don't know that it fails. I know that our proof fails.
Well, I mean, I guess the problem is this kind of surgery, right? That you indicated. I mean, that's probably the major stumbling block in higher dimensions.
Yes. Well, I have to think about a little bit about this. Where is this picture?
I mean, you caught up.
There's also this picture that I have to worry about a little bit, but certainly the surgery is the big enemy. I mean, there's other issues, and that's so even for this picture, we need planarity.
Mm-hmm. I see.
But maybe then one could say something still, but maybe it's false in higher dimensions. Like I can't say. I think I had mentioned something about this previously, and then someone from the audience suggested that maybe this is just false, but I just don't know.
Okay. Other comments or questions?
So you had this thing about PI spaces, one of your questions at the end.
Yeah.
I guess maybe I should probably have thought about this before, but is Jonas's what is so Jonas proved that in Rn, if you're a PI space, then you're uniformly rectifiable, right?
Yes.
Let's say you're not in Rn, but I tell you it's a manifold, or topological Rn or whatever, and you know it's a PI space and it's alpha is regular of the correct dimension. In other words, just your question where BPI is empty and you know it's a plane or a manifold.
Right. So you're saying replace Rn by something that's not that far from Rn, and that it's a manifold with some control.
Well, I mean, Jonas is about arbitrary sets.
I'd be scared to say anything out loud right now.
No, okay, yeah.
No, but isn't this actually true, Guy?
I'm trying to now. I don't remember. So I have a topological alpha is regular topological manifold of the same dimension.
Yeah. No, I think this is known. I mean, wasn't there a paper by Ewer and maybe Stephen Keith where they exactly proved this?
But that it's uniformly rectifiable?
Well, I mean, I don't.
The rectifiable for sure, yes.
Oh, I see. Okay, all right. Well, yeah,
so I guess one attempt would be to try and connect this to LLC.
Yeah.
Right, and then use
your
result.
Right. I mean, I misremember. Yeah.
I don't know, Sylvester, you.
Well, I was just thinking the LLC seemed. So, what was your condition? What was the exponent on the right-hand side for your Poincare inequality? It will depend on whether you get LLC will depend on this as well, because if K is greater than the dimension D, then you can have these disks touching at a point.
So here K equals D.
Yeah, okay, that would preclude. Yeah. If you have K equals D, then that precludes that. But yeah, so yeah, you cannot hope LLC condition if K is greater than D. I would guess that you would be a bit surprised if you could get LLC even with K equals D. But I'm not sure. At least contractible. Yeah, contractible seems somewhat. It seems a bit surprising.
What if k equals 1? Then
yeah, certainly not with.
I guess we'll have to switch to the next talk.
Certainly not with a too large exponent, right? I mean, even I think if k is equal to the dimension, I think you cannot expect any kind of LLC condition, right? Because you could glue things in principle along Cantor sets or something, right? Of course, this violates the manifold condition, but it somehow tells you that lower dimensional things could become a problem, right?